Today we have with us Dr. Sudha, Professor and Chairperson, Department of PG Studies and Research in Physics, Kuvempu University, Shankaraghatta. Dr. Sudha Madam has done her PhD in 1999 from Mysore University under the guidance of Professor A.V. Gopal Rao. Prior to this, she was a CSIR Research Fellow at Mysore University, joined the Department of Studies and Research in Physics as Assistant Professor. Dr. Sudha was awarded the D.C. Paute Memorial Fellowship to do the postdoctoral research in development of applied mathematics and theoretical physics, University of Cambridge, UK. Madam's area of research is quantum information science, theoretical aspects. She has published more than 50 research papers in reputed international journals, guided 6 PhD students and 3 MPhil students, presented papers in several national and international conferences and workshops. Dr. Sudha Madam is a part of DST-funded consortium-based project QUEST, Quantum-Enabled Science and Technology, and successfully completed the project as co-investigator. She has worked as coordinator of All India level 15-day workshop on physics training and talent search conducted at Kuvempu University. Around 47 students from different parts of the country participated in this workshop. The workshop was funded by scientific institutions such as HRI Allahabad, IMSC Chennai, TIFR TCIS Hyderabad, Science Education Panel, Indian Academy of Sciences, Saha Institute of Nuclear Physics, Kolkata. She is the chief editor of Kuvempu University's Science Journal published by Prasaranga, Kuvempu University. She has published many articles, among them Science Needs Women is published in Commonwealth volume. Visualization of Women in Media, Literature and Science published jointly by Prasaranga and Women's Resource Center, Kuvempu University during 2012. She has published many biographical articles in Kannada on scientists. Bauta Vignanada Adbhuta Chetana, Vignana Karnataka, Prasaranga, Mysore Vishwavidyalaya, Rupakagala Preethiyannu Meerida Chaitanya, Stephen Hawking, Samajamukhi Masapatrike, Vignani Stephen Hawking's ಮಹತ್ವದ ಪ್ರಶ್ನೆಗಳಿಗೆ ಸಂಕ್ಷಿಪ್ತ ಉತ್ತರಗಳು, Samajamukhi Masapatrike. This is the review article in Kannada on the book entitled Brief Answer to the Big Questions by Professor Stephen Hawking. With this big background, I welcome Professor Sudha Madam to deliver a talk on quantum science and technology, a bird's eye view on origin and development. Over to you, Madam.
Thank you, Dr. Anand. Am I audible?
Yes, madam.
Yes, madam. Yes, madam.
Is visible?
Yes, madam. Visible, madam.
Yeah. Thank you. Good evening to my bestly greetings to all of you on the occasion of National Space Day. Many teachers here might have organized programs and celebrated the success of Indian space mission. Here we are yet to celebrate, but the central government has given us a breather that the programs for the Science Space Day can be celebrated throughout the year. We are planning to have good programs like essay competition, inviting resource persons from ISRO and other space organizations. Hope it will realize. Before beginning my talk, I wish to thank KSDA, Dr. Ramesh, for giving me this opportunity. Thank you, sir. I'll first give you the outline of my talk. I'll mainly discuss about the history of growth of quantum science, leading to the present-day quantum information science and technology. I'll also give chronological details of development of quantum technology. I'll not go into the details of the technological aspects. Professor Usha Devi has dealt with them, and also Dr. Akshata has dealt with them in some detail in the first and third talks of the series. I also wish to brief about in the second part of my talk I wish to brief about the cloud computing platforms developed by IBM and other companies. If time permits, we will show some simple problems illustrating how to work with the quantum processors available on cloud computing platforms.
Madam,
It's a pedagogic one,
sorry,
believing that it is. Am I not? Is there any problem?
madam, have you changed the slide, madam?
No, I'm yet to change the
Yes,
slides.
yes.
I'm just
Wanted
like
to-
it's
just wanted
a
to check.
beginning. Yeah, I'm yet to change the slides. Okay.
Okay.
Yeah. Uh, yeah. I'll start my talk with a picture, a pedagogic illustration of the distinction between the continuous and the discrete. I'm sure it is self-explanatory. Now, coming to the so-called first revolution or the origin of quantum science, I'm sure most of you are aware of the details. I'll quickly browse through them, mentioning any interesting detail here and there. There are three stages in the development of quantum mechanics. The first stage is 1900 to 1912. The heroes of the first stage are Max Planck and Albert Einstein. Second stage is from 1913 to 22. Niels Bohr is considered as the sole pioneer. Third stage, it's 1923 to 27. Starting with de Broglie, it is Heisenberg, Schrödinger, and Dirac. Yeah, about physics in 19th century, towards the end of 19th century, that too after Hertz's illustration of, experimental production of electromagnetic waves, people believed that classical physics, we all know what classical physics is. It's classical mechanics, classical statistical mechanics, and classical electrodynamics. Scientists believed that it explains everything about nature. Some new discoveries towards the end of 19th century, very important ones, radioactivity, X-rays, and discovery of electron. In fact, as I said, scientists believe that classical physics is the theory of nature and everything. Here is an interesting reply of John Philip, Max Planck's teacher and mentor. Max Planck has asked him in a letter asking for advice whether he should seek a career in theoretical physics. Here is the reply. Why do you want to ruin your life? It's almost, theoretical physics is almost practically finished. Is it worthwhile taking a job which doesn't hold any prospects for the future? This letter of John Philip reflects a belief held by most scientists at that time. They thought that a final description of physical phenomena was at hand. In fact, it was not. Nature laughed at their complacency. There was a lot to come by. Coming towards the end of 19th century, there were several experiments which could not be explained by classical physics. We all know these: black body radiation, photoelectric effect, line spectrum of hydrogen, specific heat of solids at low temperature. These four led to the quantum physics, whereas the fifth one, it led to the special theory of relativity by Einstein. Here is the famous black body radiation formula by Max Planck. He has arrived at this formula on a Sunday evening of 7th October 1990. His experimentalist friend, Reuben, visited him for a tea, and then he discusses with him about the low frequency behavior of black body radiation and the matching of the black body radiation curve with that of the Rayleigh's formula. Till then, Max Planck had believed that Wien's, the high frequency region behavior of black body radiation, and Wien's formula for it explains the whole spectrum. This came as a surprise, the experimental result, as well as Rayleigh's matching, the formula matching with it. He immediately sits down to reconcile with the two limiting forms and arrives at this famous formula. He had to invoke the quantum nature of light, that absorption and emission takes place in a discrete manner, not continuously. His paper, The Theory of the Law of Distribution of Energy in a Normal Spectrum, is presented by him at Berlin Academy of Sciences on 14th December 1900. It can be labeled as the birthday of quantum mechanics, and Max Planck is the father of quantum mechanics. But Planck himself was not convinced about his quantum hypothesis, and many of the scientists also. Einstein comes to the support in 1905. In fact, Einstein deals with, he comes to know of the corpuscular nature or particle nature of light in two different circumstances. One is the well-known photoelectric effect. The other is he was analyzing volume dependence of the entropy of black body radiation in the high frequency limit. The high frequency limit is the matching with the Wien's formula. He got the corpuscular nature of light there. And there are two situations where he encounters the particle nature of light. He names these light particles as needle quantas. The name photon was given by chemist Jean Louis later, not in 1905 and not by Einstein, much later in 1926. Then again, Einstein in 1907, he explains the variation of specific heat of solids at low temperature. The atoms in a solid are quantum simple harmonic oscillator, and they absorb energy in quantas. This explains the low temperature, the decrease of specific heat with temperature. And then again in 1909, he works on Planck's law to calculate the energy fluctuation of radiation. Then he comes to, he arrives at the result that Planck's law is a sum of two terms, one of them corresponding to high frequency Wien's law, and there, as I already said, arises particle nature of light. The other one is corresponding to the low frequency Rayleigh-Jean's law, and that corresponds to the wave nature of light. Thus, he concludes that radiation described by Planck's law has both classical wave-like nature as well as quantum particle-like nature. He thus establishes wave-particle duality of radiation. One can say, not probably in 1905, in 1909, the wave-particle duality of radiation, a theoretical, both experimental. It came to, it got founded. The second stage in the origin of quantum mechanics, this is a journey towards atomic model. Giger-Marsden experiments of alpha scattering. They were students of Rutherford, and Rutherford was keenly watching the results of their experiment. And you all know what the alpha scattering experiments, the results, recoil of alpha particles, very few of them get they come back, and all else pass through unaffected. And he comes up with his planetary model of an atom, a classical one at that. It means that electrons revolving in an orbit, they emit radiation and collapse into the nucleus, and which is not seen. Atoms are seen to be stable. And then comes Niels Bohr, comes up with his model, the planetary model with non-radiating orbits, quantized energy levels. His formula, it's an immense success that it gives a perfect agreement with Rydberg's empirical formula and even the value of Rydberg constant. Soon after Bohr's atomic model, the Bohr's atomic model got experimental. Its experimental verification was through the earlier done line spectrum Balmer series in the visible region. After Bohr's atomic model, just the next year, 1914, Frankel's experiment, a very innovative experiment that proves the Bohr's atomic model, and he gets Frankel in 1927, and then Sommerfeld, elliptical orbits, Debye and Sommerfeld, angular momentum, and the Bohr's correspondence principle, Stern-Gerlach experiment. Niels Bohr gets his Nobel Prize in the year 1922. I wanted to mention the day 7th October 1900 happens to be the 15th birthday of Niels Bohr. Niels Bohr was a young boy, 15 years young boy when quantum theory was born. Yeah, the success of Bohr's theory is evident, but now the work initiated now means several years earlier also, after the quantum mechanics, the actual quantum mechanics was born after Schrödinger, Heisenberg and Dirac. The work initiated by Niels Bohr is termed as old quantum theory. Still, it doesn't take away the credit from that work. Here are the three heroes of the old quantum theory: Planck, Einstein and Bohr. And then the actual quantum mechanics, the growth of quantum mechanics. Incidentally, the name quantum mechanics was coined by Max Born. I don't know what it was called earlier, but whatever we now call quantum mechanics is the name. Wave mechanics also we call Schrödinger's wave mechanics. The term quantum mechanics was coined by Max Born. The beginning of the third stage is Compton's experiment. He establishes the wave particle duality of, sorry, I've written around this thing, wave particle duality of matter, radiation beyond doubt. And then comes the, a logical thinking. If light, which is considered as a wave, has a particle nature, why not massive particles which have particle-like nature not have a wave-like nature? And then comes the de Broglie's formula for wavelength of massive particles. And its confirmation through electron diffraction experiments, Davison and Germer, they even prove the formula lambda is equal to h by t. And G.P. Thomson's experiment, and G.P. Thomson is the son of J.J. Thomson, who discovered the electron as a particle, whereas his son proves that electron is a wave. The illustrious father-son duo, both of them are correct. Now comes the real growth of quantum mechanics, I should say. The year 1925 to 1926, a very fruitful but dense years. Here is a quote: "Never in the history of physics has so much been achieved by so few in such a short time." Yes, all the three formalisms, Heisenberg and then Dirac and Schrödinger formalisms, developed during this period and a bit into 1927. Here is a small story about Heisenberg formalism. During May-June 1925, Heisenberg was down with something called hay fever. I don't know how contagious it was, maybe like our COVID. He isolates himself somewhere, and then during that period, he thinks of the developments, and he comes to, his thinking was that electrons' position and momentum, which were earlier considered as numerical quantities, are arrays, each entry corresponding to transitions between two different states. He didn't know what his array was. He didn't know about matrices. Later, Max Born had learned about matrices, and he tells Heisenberg that what you have constructed are matrices. In fact, Heisenberg, before Max Born's revelation that these are matrices, he had come up with a multiplication rule of his arrays, which matched with the matrix multiplication rule, the well-known matrix multiplication rule. Heisenberg, along with Max Born and Jordan, formulated matrix mechanics. Generally, even if it is referred to as Heisenberg formalism, the contribution of Max Born and Jordan, all the three Germans, their contribution was significant. Then, July 1925, Heisenberg gives a lecture in Cambridge. His host was R.H. Fowler, He was Dirac's teacher. It seems Dirac missed the lecture, but later Heisenberg had discussed about his work with Fowler and sends him the proof sheets of Heisenberg's paper, his own paper on matrix mechanics. Fowler hands it over to Dirac to look into it. Dirac ponders over the results, but he was not initially convinced. But immediately, within a week or so, he realizes the immense significance of Heisenberg's work. Actually, Heisenberg was unhappy with his own, during his matrix multiplication and all, he comes up with the diagonal elements of QP as non-commuting. QP minus PQ is equal to H cross was the thing that he got. He was very unhappy about it. But Dirac comes to realize the significance of non-commutivity soon. He, along with coming out with a more flexible form of quantum mechanics, he considers the feature, the non-commuting nature, as a very significant and fundamental feature of quantum mechanics. And he comes out with the conclusion that classical limit of commutator is Poisson bracket. His results also, they get published even before 1925, a very fruitful year. During 1925-26, Schrödinger enters the picture. Schrödinger was much older than both Dirac and Heisenberg are contemporaries, a year or apart. Schrödinger was much older. He was inspired by Peter Debay's comment about the developments that Peter Debye says that in a seminar that there is a connection with eigenvalue problems of some differential equations. The equations of motion of the waves, matter waves, has some connection with eigenvalue problems of some differential equation. This inspires Schrödinger. In fact, we all now know that the time-independent Schrödinger equation is nothing but an eigenvalue equation in the Hamiltonian. He too was on a vacation. Schrödinger did his most of his work on a vacation, Christmas vacation during 1925-26. His 6 landmark papers kind of established wave mechanics. He also proves the equivalence and Heisenberg's formalism through this paper. Yeah, here are the 3 papers in the chronological order. Heisenberg first, Dirac then, and Schrödinger. A bit more about Dirac. Here is a biography of Dirac, the strangest man, the hidden nature of Paul Dirac, a quantum genius. In fact, here is an interesting thing. Dirac was to introduce Heisenberg to an audience at ICTP Trieste, Italy. He says this: we were students working in the same problem at the same time, but he succeeded where I failed. It's a surprising statement. It seems Dirac probably thought that Heisenberg succeeded and he failed. I don't know. I'm just thinking that probably because Heisenberg came up with his formalism of quantum mechanics first. Don't know. There is nothing to consider that Dirac is a failure or that his opinion is not supported, his own opinion of himself. Yeah, another, his nature. Niels Bohr and Dirac, he says this: of all the scientists, he is the finest human being. Such an accolade from another fine person, Niels Bohr. Dirac was a man of very few words. This book, a very interesting book, it's available in Amazon and other platforms. It quotes several instances of Dirac not at all speaking unless it is so warranted. I hope some may be interested to go through the book. A personal detail: Dirac married Wigner's sister. She was a divorcee and a bit elder than Dirac, I think. Yeah, that's a personal detail. And then comes the interpretation of quantum mechanics from 1927 to 1930. Born's interpretation of wave function, Bohr's complementarity principle, Heisenberg's position and momentum uncertainty relation, its improved derivation by Robertson, Schrödinger, and Weil. And the last but not the least, most important, is von Neumann mathematical framework of quantum mechanics. This played a significant role in the development of the quantum information science and And from these thoughts, the standard or Copenhagen interpretation of quantum mechanics emerged during this period. This is the one we teach in our BScs and MScs, though probably not mechanics. Though several were unhappy, Einstein, Schrödinger himself were unhappy with this formulation. Two survey conferences happened during this period, 1927 and 1930, and the very famous Bohr-Einstein debates. Developments after 1930, yeah, I already said Schrödinger and Einstein were unhappy with the Copenhagen interpretation. In fact, Schrödinger's cat experiment, he thought over that to kind of oppose to illustrate the logical inconsistencies he felt was the collapse of wave function postulate of Copenhagen interpretation. It's not kind of an illustration of quantum entanglement or anything. It was an experiment thought by Schrödinger to mention and describe his dissatisfaction with Copenhagen interpretation. And here is an important paper, 1930, von Neumann's paper, and he proves a theorem much before, like 5 years earlier than Einstein's work. Von Neumann says that quantum mechanics doesn't need it's impossible to embed quantum mechanics in a more complete theory. He proves that theorem. See, just 1935, Einstein comes up with the result that quantum mechanics is not a complete theory and it needs embedding in some more complete theory, the presently called hidden variables theory. Einstein probably was unaware of von Neumann's theorem. He doesn't give any reference to von Neumann's work. Yeah, here is a biography of Albert Einstein, Abraham Pius. Abraham Pius is also the biographer of Niels Bohr. We all know Einstein's firm belief was that God doesn't play dice, his dissatisfaction with the probability interpretation. And this is a conversation between Abraham Pius and Einstein in an evening walk. The realist interpretation that moon does exist even when we do not observe it. Yeah, after 1935, David Bohm, this too is very interesting. He comes up with a classical realist interpretation of non-relativistic quantum mechanics. It's a realist interpretation, somewhat kind of a hidden variable, somewhat resembling the hidden variable theory that Einstein thought of. It's in other words, may not be hidden variable theory. It's a realist interpretation. That was in apparent contradiction to von Neumann theorem. And Bohm's work, it has an important role. It prompted Bell to, it definitely violated von Neumann's theorem. And Bell thought over it. How did it violate von Neumann theorem? He looks into the von Neumann theorem in greater detail. He comes up with his own a result matching with that of von Neumann, that there is no theory which can embed quantum mechanics and the local realism and local realistic view of nature, which Einstein professes, is not correct. his famous paper in 1964. I said Eisenbridger well examines the von Neumann's theorem in a much greater detail, and he comes up with, yeah, I'll tell that in a few minutes. And yeah, these are the experimental tests, the very famous Clauser, Allen aspect, and all. Two of them get their Nobel Prize, along with Seilinger, who experimentally proved the quantum teleportation. All the three were experimental. It's a prize for doing such phenomenal experiments. Yeah, as I said, there was a great debate on von Neumann's theorem. The debate was not then when von Neumann or J.S. Bell worked on it. Bell, in fact, identifies a fault in von Neumann's theorem. He says it's not just a flawed proof, it's a foolish proof, he says. It was widely accepted then that the von Neumann's theorem is not correct, it's a flawed proof, etc., etc. After 80 years after the von Neumann's theorem, two of the scientists, I have quoted here, they come in support of von Neumann and kind of challenging Bell's interpretation. And interestingly, these two people's defense of von Neumann was challenged by Mermin and Schock. The title of the paper is interesting. Homer nodded, von Neumann's surprising oversight. It's an interesting title. They challenge the defense given by these two scientists on von Neumann's theorem and its proof. And again, a 2021 paper, which says, I will rather read that out. He says that, the author says that the two scientists who were in defense of von Neumann, their reassessment is quite correct. And he quotes some theoretical results wherein he can show that their reassessment is correct. Probably the debate is still going on. Any talk on quantum information theory is incomplete without mentioning the father of information theory, Shannon. Such a genius, words won't suffice to describe his genius and his persona also. That's why I won't do it. I'll just tell you a very few things about the importance of his 1948 paper, A Mathematical Theory of Communication. He's an American mathematician, computer scientist, engineer, cryptographer, and all that. It's an electrifying paper when he was just 32-year-old researcher at Bell Laboratories. Let me just tell you about the significance, how others describe the significance of Shannon's work. It's called Magna Carta of Information Age, a blueprint for digital era. And more interestingly, it is considered profound and fundamental than transistor. Transistor was discovered during the same period in 1947 at Bell Labs, and it was considered that Shannon's information theory was more fundamental than transistor. I just given the formula of Shannon's entropy and then its generalization to quantum entropy, the von Neumann entropy. As I said, it's very difficult for me to describe in few words about Shannon's ingenuity and his genius and whatever one calls it. I've just given one or two articles which I very happily read and felt so good. These are the two articles. Both of them were written when during 2001. Yeah, when Shannon passed away. Very interesting articles. Please, like somebody who is interested can go through it. And see, quantum information theory is called as quantum Shannon theory, like that itself signifies Shannon's importance of Shannon's work. This is a book by Mark Wade. It's available in the archive. It's a technical and very like a very good book for anybody who wants to study quantum information science in detail. Yeah, now comes the development towards quantum information science and technology. Here comes an interesting paper. It's one of the first attempts at creating quantum information theory, that is a generalization of Shannon's classical information theory. A person from Poland, like Poland is considered as the intellectual hub and all that I have heard. Look at the argument or the result that this paper shows. He says a straightforward generalization of classical information theory by Shannon is not possible for closed quantum systems because the usual quantum theory of closed quantum systems doesn't contain joint and conditional probability. But a generalized quantum mechanics of open quantum systems, Kosakowski et al. Are the pioneers of that concept of open quantum systems, leads to the straightforward generalization of Shannon's theory, a very significant paper. And then during 1980, the quantum mechanical model of Turing machine. Turing machine, I should have mentioned about Alan Turing also, like his idea of Turing machine and then just Turing hypothesis and all that are the beginning of the first result to demonstrate the possibility of quantum computing during 1980. And then, like we all know, Richard Feynman's obsession with computers. In fact, he was even much before, I think during 1944, Feynman was then a junior staff member at Los Alamos. He, it seems, has organized a contest between people, human computers he calls them, and the Los Alamos IBM facility. Not a computer, they are punched card machines. The IBM facility, punched card machines, with both performing a calculation for the plutonium bomb. People like people who are working on it, their pace goes down and down as in 2 or 3 days, whereas the punch card machine operation, it goes with a steady pace, like then illustrating. And we all know that it was his fascination with the quantum computing. And then he comes up with his 2 papers. One is the most well-known, Simulating Physics with Quantum Computers, and this is the title of his talk also at Physics of Quantum Computation Conference. That paper is 1982, I think. Yeah, Simulating Physics with Quantum Computers, that is. Yeah, he puts forth the idea that classical computers do not have the potential to simulate physical phenomena, whereas a quantum computer has. His another paper, I think 1985, yeah, it's quantum mechanical computers, not much quoted, I believe. Yeah, it's his 1985 paper. Sorry. And further development, milestones in quantum information science and technology. These are 1985, David Deutsch formulates a description for quantum Turing machine. Actually, the title father of quantum computing is often attributed to Deutsch. His contribution was significant to the development of theoretical framework and principles of quantum computing. Feynman also is considered, like there are 2, 3, I think, Bennett, Deutsch, Feynman, And then comes the famous Deutsch-Josa algorithm, the first example of a quantum algorithm that is exponentially faster than any possible deterministic classical algorithm. Here I wanted to say it's 1992 to 1996, 98, each year being very significant in the advancement of quantum technology and information science. 1993 is the first paper by Bennett et al. Describing the idea of quantum teleportation. This is the famous paper. 1994, Shor's algorithm, and this is the paper, prime factorization of an integer, and it has been discussed probably by Akshata and in some detail by Dr. Usha Devi also. And then again, Peter Shor's paper on quantum error correction. Here, this too is a very important paper. What is quantum error correction? I'm not going into the details of it. I'm just for the uninitiated. Quantum error correction is a set of techniques used in quantum computing to protect quantum information, because there are several errors possible due to decoherence and other quantum noise. Quantum systems they lose their quantum property due to decoherence and other noise. There needs to be some correction to be done. A fault-tolerant quantum computation is needed, and quantum error correction is one of such. A development of quantum error correction course is an active area of research starting from 1995. And then comes the Grover search algorithm. This too is a well-known, well-used database search algorithm. About Grover. Grover is an Indian-American computer scientist. He did his graduation in IIT Delhi, and then he moves over to Stanford University and then Bell Laboratories and all. 1997 this is the most important work, experimental work, which got Zeilinger his Nobel Prize. First demonstration of quantum teleportation. And then in 1998, this is the first demonstration of quantum error correction. Within just maybe 1995 is the paper theoretical result on quantum error correction, and then is the experimental demonstration of quantum error correction. 1999 is the experimental demonstration that a superconducting circuit can be used as it. We now call it a superconducting qubit, SC, we call it. By Tokyo University, scientists at Tokyo University show that superconducting circuits can be used as qubits. And another is the experimental demonstration of 5-photon entanglement. Pan's group in China. And China, we know, is one among the leading countries progressing towards quantum technology. And this is a work in 2004. An experimental demonstration of 5-photon entanglement. Actually, 3 or 4 particle entanglement was achieved experimentally before 2004. But 5 or more particle entanglement was an experimental challenge, and it was needed for a universal quantum error correction. So this result is a very significant result and a milestone in the development of quantum technology. And then this is another quantum teleportation over 143 kilometers, an experimental demonstration of teleportation over 143, a significant distance. And here comes the establishments of quantum compute companies. The first commercially available quantum computer is called D-Wave 1 by the Canadian company D-Wave Systems. The processors they developed was based on something called quantum annealing. I don't know quite the details of it, but the practical applicability was a subject of debate. People argued that the D-Wave systems provided a limited speed up compared to classical computers. And 2012 is the first dedicated quantum computing software company based in Vancouver. It's 1QB information technology, shortly called 1qubit. This is an emerging company. It has developed hardware partnership with companies such as IBM and Microsoft. And then this is another milestone. The teleportation efforts done by Zeilinger and Zeilinger group, both of them, and that was not completely error-free. And this, though for a short distance, this is an error-free quantum teleportation of a qubit, hence is a significant milestone. And then 2017, quantum teleportation of a single photon qubits, and this, see, it's a 1,400 kilometer from Earth to a satellite, ground observatory to a satellite, and very important result, experimental results. Here comes 2019. Google and IBM, both are companies who are rivals. One progressing to beat the other and so on. In 2019, Google claims to have reached quantum supremacy with its 53 qubit Sycamore Transmon superconducting computer chip. It claims to have performed a random number generating calculation that it takes a lot of time, 10,000 years to complete, they claim, for the best conventional supercomputer, they say. Their computer, the superconducting, the Sycamore quantum processor, does this operation in just 3 minutes, whereas the best supercomputer may take 10,000 years to complete. IBM responds to Google's claim. It was a much debated discussion between Google and IBM. IBM says that their own supercomputer can do the said task in 2.5 days. So Google's claim is wrong, they say, and their supercomputer can do it in much less than 2.5 days if some implementation techniques are bettered, they say. Thus, the quantum supremacy claim of Google is not quite taken. The present situation, a lot of computing establishments. Here is a picture, 1qubit, JP Morgan, IBM, Google, and their work is based on several drug discovery, software offerings, etc., etc. What should I say? There is nothing probably that the quantum computers and technology cannot do. It appears at the moment. I mean, it's a loose statement. I'm just highlighting the significance and importance of quantum technology in several areas of our life. And this too is startup activities and investments. So see, the investments, it's all over the world, I believe. 2001 to 2015, it was considerably less. From 2015, it jumped. This is a data from 2020 up to 2021, but the graph is not stopping. It's increasing. Like 2024, like our own India itself is investing around 600 crores for the development of quantum technology. And thus, in its national quantum mission, and that's like coming up, and 600 crores is, though others are investing more. For India, it's a considerable effort. We hope that it gives fruitful results and all. There is I'll show you later that there is a significant development in quantum technology here in India. I'll now come to the second part of my, I won't take much time here. IBM has provided with IBM Quantum Lab is an online platform. It's an online platform allowing an access to cloud-based quantum computing. We can sit at our in our room with our computer and access the quantum processors placed elsewhere and do experiments. There are several experimental demonstration of theoretical protocols has been done quantum devices. And here are some literature which gives you Qiskit. Learning Qiskit is important for working with IBM Quantum Lab, and installing IBM and working with it, Qiskit and all is available on like web. One can just Qiskit, it will give you several guidelines, like one can install Qiskit IBM Q without much difficulty. Even students are doing it. Yeah, here I want to illustrate few experiments which our undergraduate and postgraduate students can do in their own labs with their computers, and I'll show the circuits and the experiments done, and they will help the students to understand the principles of quantum mechanics in much better way. That's what is my intention in doing this part of the talk. Here are the symbols for representing the quantum gates: Hadamard gate, the rotation gate, C0 gate, and the Pauli Z gate. These are the two projectors here, which map our 0 to 0 and 1 to 1. I'll give here an illustration of generating the Bell state 0, 0 plus 1, 1. Here is the circuit implemented on the IBM Q. Here is Hadamard, and what Hadamard does when it acts on this is first qubit and this is the second qubit. When Hadamard is operated on the state starts out with the Kronecker product 0, 0 initially. The Hadamard acting on the first qubit implies it is H Kronecker product, nothing on the second qubit, and it gets Hadamard converts 0 to the eigenstate of the sigma x matrix 0 plus 1 by root 2, and this remains the same, and what we get is 0, 0 plus 1, 0 by root 2, and a C0 operation will give us the required state. C0 takes 1, 0, 2, 1, 1, not doing anything if the first qubit is, control qubit is 0, changes the second qubit if the first qubit is the control qubit. First qubit is 1, the control qubit is 1. Here is the result of the implementation, and just see, this is measurement in the Z basis. This symbol illustrates the measurements in the Z basis. That is 0 comes out as 0 and 1 comes out as 1. One can see that it is it gives out the state 0, 0 plus 1, 1 by root 2 experimentally. It's 0.5 probability nearly, and there are some errors here, and the quantum processors are error prone. The quantum processors presently available are called NISQ era, noisy implementation of quantum systems, NISQ era. Like all the processors, even NMR and presently available, are bound to have some noise effects. One has to do either error mitigation or quantum error correction. Quantum error correction needs resources So error mitigation is the process which takes away the errors that are seen here. There are several methods of error mitigation. I won't discuss them. It takes longer time. And for the second well state also, I have given the illustration of how it works. Here, Hadamard acts on the first qubit and Pauli X gate acts on the second qubit. The second qubit, Pauli X gate converts it into the 00201. Sorry, I have written it as, this should be 01. And Hadamard, we know the state becomes this, and what we get is 01 plus 11 by root 2, and then C naught takes it to the state under consideration. Here too, we can see the probabilities are nearly 0.5 with the error here. Sorry. Yeah, so those students who are, I don't know how many students are experts, please excuse me for this demonstration and all. Students and teachers can work out the generation and all that in the manner that I illustrated for the first two Bell states. Yeah, this too is the thing. One can sit and work out. It's not very difficult. And here I want I said then the measurements are in the Z basis. What I mean to say there is my state, the given state is expressed as a combination of 0 and 1s, which are eigenstates of Z. If I do a measurement in X basis, that is, if I express my state as a superposition of, in terms of the eigenstates of the Hadamard, the eigenstates of the Hadamard is readily seen to be the eigenstates of the sigma X matrices. And here is the Pauli like phase gate, and the eigenstates of S followed by H are the eigenstates of sigma Y matrices. If I measure after applying my H and then, yeah, for another experiment SH, then I will be measuring in the X and Y basis, and the results I'll show in a moment. This is a simple illustrative experiment to evaluate quantum expectation value of a single qubit state. Here, I have initialized the state. I haven't generated it. And I have measured it in the Hadamard and then measured. That means I have expressed this state as a combination of the eigenstates of sigma X. What I get here is the probability of this state to be having a result +1 and this -1. The collapse state is, after giving this result, the state falls into the eigenstate of sigma X, okay, with the +1 and -1. And one can readily evaluate in this itself, like the theoretical evaluation of sigma X. These are very simple experiment, very pedagogic. I'm just only doing it for the sake of students. Sigma X comes out to be 0.8, and with this experimental results, we get it to be 0.825, which quite well matches. And then measurement, an illustration of measurement in Y basis. And this is, as I said, SH takes the state 0 into the eigenstates of sigma Y. When I measure it, I get the probabilities of obtaining one of the eigenstates of sigma Y and the other eigenstate of sigma Y with results +1 and -1. The expectation value is evident. One can readily see that it is like almost equal probabilities, and it gives sigma Y is equal to 0, a theoretical evaluation. Measurement in Z basis is pretty simple, and there is no need to explain it. It's a default measurement. Yeah, we get the experimental results to be same. These are done in IBM Q Lima, a 5-qubit quantum processor. It's presently not available. It was probably in beta version and it has now retired, not available publicly. And several other more qubit processors are available. Yeah, I have done the same evaluation of expectation value for 2 qubit states. I have done it for sigma x cross sigma x. The evaluation of the mean spin vector of the 2 qubit state. One can see, like here too, I have measured the first qubit in the x basis. And the results I get, I mean, these are pretty evident. Here, this I did in a Qiskit simulator. We couldn't access any quantum computers, processors that time. This was done in simulator, so the error bars are not seen. There is errors, but nothing is seen here. Yeah, it's readily seen that the 2 plus eigenvalues, and I've written it wrong here, P0 plus P1, 1. Yeah, this is P0 1. Yeah, this is P0 1. And the experimental and theoretical math. Very, very simple experiments. I wish our teachers, whoever are there, take up these experiments and do it in their labs. That will kind of I get a kind of satisfaction that this has helped. Yeah, now I just browse through the tomography scheme of 2 qubit states, determining the density experimentally determining the density matrix elements of a 2 qubit states. It needs 15 parameters, the number of parameters in a 2 qubit state, independent parameters. But here is a scheme given by Shruti Dongra et al. With just 7 measurements. I don't know. Somebody is speaking. I don't know. Like, is there anything?
No, madam, please continue.
Shall I? Yeah, another 5 minutes. I won't take much time. Okay, another 5 minutes.
നമുക്ക് 11 to 12 ആണ്.
Okay, so like these are the 7 experiments, and I'll just mention these 2 can be done on. Yeah, so here are the probabilities that are obtained in each measurement. The measurement scheme is given here in each of the 7 experiments. Yeah, just measuring the state in Z basis gives me the diagonal elements, and acting the rotation gate on the first and not doing anything on the second gives me the like other elements, which the formula for which these are the experimental bar diagrams, probabilities. Oh, okay. So yeah, I hope this is a kind of a scheme that we have illustrated, and I have just given how the like one can see the theoretically also one can see working in a Mathematica also how the diagonal elements result, not doing anything on the qubits, just projecting them onto this thing Z measurement. Yeah, this also I'll just browse through this. It can be seen that the probabilities, the 4 probabilities, 2 of them give me the 1-3, the real part of 1-3, and the other one gives me the 2-4 R2, the row 2-4.
നല്ലതുണ്ടായിരുന്നു. നമുക്ക് പിള്ളേരെ പഠിപ്പിക്കാൻ പറ്റിയതാട്ടോ, അതേപോലെ പോവാൻ.
Someone is speaking, I think. Can you mute for some
Yes,
time, please? Yeah. Yeah, here is some information about the presently available quantum processors with maximum qubits. This is the data given by, yeah, as I said, these are all noisy intermediate state quantum processors, all noise ridden processors. One has to do some error mitigation protocols to avoid the, to correct the noise. This is the Nature Reviews Physics survey. They say 72 superconducting qubits for Google. They have produced, offered 72 superconducting qubits. Okay, and this is 127 by IBM. We have recently worked and collected results from this, and it is retiring in, it has already retired in August 16 or so. And these are 32 trapped ion qubits per ion cube and 20 and 80, different companies. And here is a newspaper report that atom computing has come up with a 1180 qubits quantum processor in 2023. And D-Wave also 1200 qubit quantum processor. I don't know, Nature has given, that was a 2024 paper where they have given just 80 qubits and all. And these are saying 1200 qubit. Yeah, like one can see that the number of qubits and the advantage of processors that are being developed are going, advancing a lot. Yeah, here is India's contribution to the quantum technology. At TIFR, within few days, I believe, a small-scale quantum computer will be developed by TIFR's Quantum Measurement and Control Lab. It was established 12 years ago. It took this long to come to this stage of developing a small scale, like some few qubits quantum computer. This is a project in collaboration between TIFR, DRDO, and TCS. Dr. R. Vijayaraghavan is at the helm of affairs, and this is a celebrating news for the quantum technology community of India. And I want the audience to, like many experts may know, but excuse me. Is there anything? Yeah, this is my last slide. I'm done with it. Yeah. This is Quantum Research Park, a quantum computing hub developed by, supported by, it's administered by Foundation of Science, Innovation and Development, IISc, with support from Karnataka Innovation and Technology Society, Government of Karnataka. It's conducting lot of outreach programs. Q-Daksha student internship. This is for about 4 to 8 weeks. They conduct this internship. One can go 4 to 8. They provide the accommodation and etc. for BSc graduates and postgraduate students, all from Karnataka only. And this is Q Karyashala. And here too, it spans over maybe a week or so. One can look into the website, Quantum Research Park, and go through the details. And this is for teachers and senior researchers, faculty members from Karnataka. Teachers can take note of this and send their students, and they can also participate in the outreach programs developed by Quantum Research Park. And with this, I want to thank all of you for a patient listening. And again, thanks to KSTA for the opportunity. Thank you. If there are any questions related to the topic that I have spoken about, I would like to take.
Thank you very much, madam.
Yeah, thank you.
Scholastic presentation and session. There were a few questions in the chat box, and already.
Yeah, I'll just look into them.
I was supposed to read them, but meanwhile, Usha madam has replied.
Dr. Usha is there, and probably she has answered.
Yes, ma'am.
I believe, yeah. So that's a great help. But let me see the questions. And any comments from other? Any teachers are participating in the, I don't know, the
most of
audience.
participants are yes, ma'am.
Okay, okay, okay.
Okay, madam. I'm Anand. Can I ask it out?
Yeah, please, Anand. Yes, please.
Ma'am. It was a nice chronologically arranged presentation, ma'am. If physics is taught in this way, then nobody can have to rote learn that J.J. Thomson actually discovered electrons. So even a student can remember that if we learn through the chronology, we can remember that his son actually discovered the wave nature of.
Yeah, that's a
He has actually observed the
well-known
wave
thing,
nature.
but still, yeah, many
No, 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 no,
students
no.
may
Just
not
what
be
I'm saying
knowing.
is,
Yeah. Mm.
yeah. Ma'am, I had a doubt.
Mm.
You have almost exhausted the entire development of quantum computers. I mean,
Mm.
the steps which has actually
Yeah.
went one after another. But
Yeah.
I just wanted to know where will you place Moore's law in that chronology? Because if what I have know that
Yeah. I got to know
also
your point,
uh,
like where does
Moore's
Moore's law
uh,
stand? And
stands in your
yeah, I
presentation
haven't
because.
thought about it. Yeah, I haven't
Uh,
thought about it.
Because I mean, my point of view is whether I think the growth of looking towards quantum computation has actually accelerated because of his ideas. I think so. I mean, what is your opinion, madam?
I'll
If his
examine
law is not
Anand.
there, if his law is not there, then also quantum computation or IBM, do you think
Yeah.
they would have
Quantum
taken a step?
processors in general, not just IBM,
Yeah,
not just IBM.
yes, exactly. I mean, if
Yeah.
it is not there, the funding
No,
and all, which is,
yeah. You please, you are also capable. You too are an expert, can look into it. Meantime, I'll also look into it, to the,
not
yeah, where
immediately,
does
just I
Moore's law
wanted your
stand here?
opinion. If he doesn't given his, I mean, if there was no Moore's law as such, then is there any effect on the growth of quantum computation
Yeah,
field?
I'll look into it, Anand.
Can
Anybody,
I intervene?
please,
Shall I
please,
intervene?
please.
Anand, what I had
Ma'am.
shown in a picture, I had shown
Uh,
that Moore's law doesn't help if you have
uh,
progress in
uh,
classical computation also. So that is, it won't help
okay.
you in solving some problems
Mhm.
which were polynomially hard. That is,
Mhm.
NP hard problems cannot be solved even if you have Moore's law helping. That is, number of systems reduced and all that, whatever you do, Moore's law doesn't play any role.
Thank you,
So
ma'am.
in such
That
a
is all.
case, so you have to think about whether one should look at Moore's law or kind of
Mm.
focus on whatever
Mm.
needs to be done right now. Because it has
Okay.
already been seen that if you
Mhm.
project whatever is known and
Mhm.
extend your, say, what can a classical computer do in the Moore's law regime itself, it wouldn't help.
Mhm.
That's what
Mhm.
is seen in exponentially hard kind of problems, computer science problems. That's what I know.
Mhm.
That's all. Okay.
Thank you.
Thank you.
Thank
That's
you.
what I wanted to ask.
Anyone else?
Any other questions?
Yeah, Dr. Sudha, thank
Yes,
you
sir.
for a nice
Please.
lecture.
Thank you, sir. Thank you.
Yeah, I really wanted to know more about the kind of work which you have done with IBM. You may call it, I mean, mostly for students. I think many of us, at least I am not that much, very much familiar with the use of this. In regard to what you have done, my question would be to know whether we can implement time evolution, I mean, include an interaction and see how a system develops over time, and then look at the state from whatever IBM is giving us.
Oh, certainly don't have any idea, sir. Certainly don't have any idea.
Sir, I can try to address it. There are some models, model Hamiltonians and time evolution being simulated by IBM. So we have not done it, or Sudha, we were trying to do tomography.
Audio gets sometimes interrupted.
Sir, are you able to hear me?
No, sometimes the audio gets interrupted. I don't get the audio. I started hearing, but somewhere. Can you kindly repeat?
Yeah, there are some, say, Ising Hamiltonian and some specific Hamiltonians are used to simulate quantum dynamics by IBM. Could you hear what I said, sir?
Yeah, I could hear now.
But
Right.
not all. But
Ah.
that is, if I want to do, it is possible. That's all is the assurance. Because what we have is a universal quantum computer in the sense that you have all the required gates. It's your design and you can do is what is the assurance. But have I done it? If you ask me, no, I haven't done it. I still have to develop much skills with quantum language, that is the Qiskit language, Python program, and how to implement it and so on and so forth. It's not quantum mechanics, but using the Python program and implementing it in Qiskit and then in IBM. That's what is the main task. So we have only done tomography, basically.
Presently, we are doing tomography. In fact,
I understand.
Yeah.
My comment would be, see, this kind of practically handling quantum computation will also provide a way to understand how, I mean, the basics of quantum mechanics also. So for those who are more motivated towards understanding quantum mechanics practically, I think this can also be a supplementary way of, help it can give. Am I right that way?
That's what is the intention of presenting these, like very simple ones. But I wish our like undergraduate and somebody said in one of the earlier talks that they have quantum information theory in their curriculum. Some undergraduate, I don't know, from Bangalore or so. So in case if they have, few lab experiments may help. Like these are the very simple ones that I have given. One can do tomography also. Yeah, that is my intention.
Sir, I will add to the discussion. You remember there was a quantum mechanics book with a Mathematica, for Mathematica. And there was a CD with using which we tried to kind of understand tunneling and all other things using that Mathematica program. I hope I am heard.
No, I know.
So such Mathematica, quantum mechanics and Mathematica or some such book was there. We were trying to see if that helps students for understanding quantum mechanics. We are in the similar situation now. Without telling more of quantum laws, if they learn it and then you teach them, it's like our arithmetic, like Maggi Kaliyodu, and then doing the program and then learning it in mathematics properly. That kind of approach may work with younger generation is what I think sometimes.
Yeah, sure. Because I could see some comments here. There are people who are intrinsically engaged with the philosophical part and all that. Maybe if they also get initiated to these practical skills, they themselves may get, the doubts may get evaporated.
Yes, sir. Yes, sir. Yeah, true.
I would say young students would certainly be getting benefited.
Yes, sir. That's what is the intention. Thank you. Thanks for the comments.
Thank you, Usha. Thank you, Sudha. Both of you have been
Yes, sir.
very
Yes, sir.
helpful.
Thank you. Thank you.
Thank you, Professor K.S. Malay, sir. Thank you, sir. Any other comments or questions?
I just want to say something
Please.
to the audience that KSTA is presently on to developing a strategy paper to make Karnataka to give a proposal to Karnataka government to develop Karnataka into such a way that it's a sought after state for quantum technologies. We are formulating it, and I'm looking into the public outreach activities, like what can be done so that our students get more interested, students, teachers get more interested, so that they can later develop their skills and join either the research field or the technological field, and that is what is the intention. Yeah.
Madam, thank you very much for a very nice talk. I joined a little bit late. It was very useful for the students who are pursuing the physics at degree and master's level. And today we are concluding this webinar series. All the 5 talks were wonderful, and experts took a lot of pains in making this subject easily understandable to the students, especially the degree and PG students, so that when they pursue their higher degrees, like they pursue their research in PhD or MPhil, these talks would really inspire them. Right from the beginning, Dr. A. Usha Madam gave a talk on a tale of quantum information science on the first day, 19th August. Followed by that, Dr. H.S. Karthik gave a talk on reviving quantumness, 2 instances of repowering protocol. After that, on 21st, Dr. Akshata Shanai gave a talk on quantum cryptography. And yesterday, Dr. Prabhu gave a talk on a few things about quantum systems. And today, Dr. Sudha Madam delivered a talk on quantum science and technology, a bird's eye view on origin and development. I'm sure students would have got a lot of take-home message, and they would have broadened the horizon of their knowledge in this emerging field. As rightly told by Dr. Sudha Madam, KSTA is bringing out a strategy paper to make Karnataka as one of the premier destination for quantum technology development, like in other fields like information technology, biotechnology, nanotechnology, and others. And Karnataka has always been at the forefront of technology development. In fact, we are very proud that Karnataka is the first state in the country to bring out a startup policy as well. So we are making a comprehensive strategy paper and submit to the government, and later I'm sure Karnataka government will take right steps to develop quantum technology in Karnataka state, as Karnataka is the science capital of the country. We would like to maintain the same tempo, and the quantum technology will certainly proliferate well under the government's support. With this, I thank all the resource experts who have delivered excellent talks, and also our associates, KCP Science College, Dr. Girija is there with us. Thank you, Dr. Girija. Usha Madam is there. Madam, thank you very much. Because of Madam's initiative, we planned a webinar, and we would like to plan second series of webinar little bit advanced than the present basic information. We may plan in September, so that students will get little bit more information on as to what research topic they should choose for their research, and also a few of them may be interested in starting their own startups. For them also, we should plan some programs. Thank you very much, Madam. Sudha Madam, thank you very much.
Thank you.
Thank you.
Malesh is there with us, senior physicist. Malesh sir, thank you very much. Your presence always inspires us. We look forward to your encouragement for KSTA programs. Dr.
Sir, thank you very much. I am so happy that these people, I have been associated with Dr. Usha and Dr. Sudha. They are dynamic, so dynamic, and I'm hopeful that they will also make most of other young, future promising MSc girl students also to join their path, and certainly we can look forward for a very bright,
Yes, sir.
environment in future. Thank you, sir, for mentioning me. I'm just a listener here. Thank you.
In fact, Usha Madam is the driving force for all our quantum programs. Thank you, Madam.
Thanks for involving me. Thank
I
you.
request all the participants and speakers to turn on their video for documentation purpose. We would like to take a screenshot for 30 seconds to 40 seconds. I request all the audience.
I also thank our Dr. Abhishek and other senior faculties, Dr. Girish, Dr. Shivalingappa, Dr. Girish, Dr. Shubha, Dr. Yashoda, Dr. Zina, and all these senior faculties have been with us for the last 5 days. Thank you very much for your presence, Dr. N. Nallamattu. I think he has joined today. Thank you very much. Dr. Zina, Abhishek. Hello.
Abhishek or illa sir?
Okay. So,
See
Dr.
Professor
Girish,
Kagli also,
Yeah, Professor Tagli is there. Yeah.
there, BAK.
senior
So thank you.
physicist. Sir, Kagli sir, thank you. Request to all the participants. Dr. Zina, hello. Dr. Girija. Hello. Our associates also should open their camera.
If it is inconvenient, we request them to drop, but if it is convenient, you can turn it off, turn it on. So we would like to take a snapshot for
Yeah.
documentation purpose. Thank you very much.
Aita, Umesh?
Yes, sir. Now
Oh,
the feedback link will be shared. I request all of you to please provide the feedback link before tomorrow first half.
thank you, Dr. Soumya Sajjan. Thank you, Dr. Yashoda. And all the participants. Thank you, Dr. Soumya. Thank you. Thank you, Mr. Arun. Dr. Gururaj is there. Thanks for all of you for being with us. As I requested, Usha Madam will be planning the second series of quantum technology webinars. It will be a little bit higher, and I'm sure those who are doing their PG program will be benefited by the talks. I request all of the teaching faculty to encourage your students to join the webinar so that they will get some good information on this emerging field. And KSTA would like to have one physical meet also. We'll be sending the flyer. The interested people can join at KSTA office. Thank you. Thank you very much.
Thank you very much, one and all. Please submit the feedback form before first half of tomorrow.